Hello everyone, and welcome to this video on building linear models or linear equations from verbal descriptions. Whenever you see the word models come up in mathematics, usually means some sort of equation or a system of equations or inequalities that are describing a situation laid out in a word problem, some application problem. Alright, so what I have for you here today are a couple examples with several parts of just scenarios where a linear model or a linear function can be applied to help answer questions about that particular situation. Alright, so let's get started. So my first example, just got the wording here. So it's already stated, my second example, it isn't stated right away that you're going to be using a linear function, but we're going to end up in it eventually. Alright, so in the linear cost function, c of x equals, ax plus b. If you want to replace a with m, that's fine. Remember, this is the slope of the line, so that a is the same as m, right? That's the slope. C of x equals ax plus b, so input x and the output is c, or c of x. Input x, output, ax plus b describes how you get your output. All right, in this function here, cost function, that lowercase b represents the fixed costs of operating a business, right? So just the cost of running the business day to day without producing anything, right? So if you were to produce nothing, and you'll see x represents the amount of product. If I produce nothing, see the cost of just running the business day to day is b, dollars or pounds or whatever units of money we're talking about. Balboas. So b represents the fixed cost of operating a business. And a, right, the lowercase a, which again you can replace with m if you'd like, represents the costs associated with manufacturing one additional item. All right, and I'll talk about that down here a little bit. Right, I've talked about how a here is the slope, this lowercase a. So again, if you want to call it m, b, that's fine. Remember, the slope of a line is a ratio, right? It's the ratio of rise to run, where some other way you might see the rise denoted as how much am I changing up and down. It's the change in the dependent variable, or the change in y, divided by, and then the run is your horizontal change, or the change in the independent variable, the change in the input, which in most cases is x. Now in this particular example here, this would be the change in c, right? Change in cost divided by change in x. The input is x and the output is c, right? Instead of x and y. So it would be the change in c over divided by the change in x. Oh, and by the way, that's what this little triangle symbol means. This is the Greek letter delta, right? So you might see people say delta y divided by delta x, or delta c divided by delta x. And whenever you see this, for the most part in mathematics, delta means change in, right? So it's the change in y divided by how much it changes in x. And in word problems, slope is not only a ratio, but it's also a rate, where there are units involved. I'll make that little note as well. So in word problems, in applications, typically slope, I'll say, because maybe not always, but typically slope is a rate and involving units. right? Let's think about that here. Look at my my slope, this A, right? So A is again, this change in cost divided by the change in product developed. The change in cost, C, divided by the change in item manufactured. All right. Now I'm going to keep reading here so we actually can get the units. What are the cost units and what are the item units? So suppose that a bicycle manufacturer has daily fixed costs of $2,000. So that's the B, right? B is the fixed costs of operating the business. This daily fixed costs of $2,000, that's the lowercase b value, right? And each bicycle costs $80 to manufacture. Additionally, the business must pay a tax of $1 per bicycle produced or manufactured. So in total, it costs them, $80 and then plus another dollar, right, in tax to produce a single bicycle. So it's going to cost this company, this business, $81 to produce a bicycle, for each bicycle. All right, so my rate here, the A, the slope of this linear function, the change in cost over change in bicycles. This is going to be in dollars, the costs, and down here the change in X. X is representing the amount of bicycles produced, right? So this is just in bicycles. Oops, can't spell bicycles. Right? So the value of A is going to be a rate of dollars per bicycle. All right, so we'll get to that on the next page. But so keep this in mind when you do slope. When you're talking about the slope of a linear function in a word problem or an application, usually there are units involved, and there are a unit for the numerator quantity and a unit for the denominator quantity. Here it is dollars per bicycle. All right, so this is I have several questions involved with this, several parts. So the first of these, I'm going to cover up this stuff about the slope here, so take a good look at it or go back in the video if you want. So part A, I'm asked to write a linear function that expresses the cost C of producing X bicycles in a day, right? And they gave me the model up here. All right, so the cost of producing X bicycles, C of X, right? This is the cost of producing X bicycles in a day, equals. Now, I told you the value of this lowercase b, right? The fixed costs, it's costing them $2,000 even if they don't produce anything, right? That's just for equipment or, property value, renting out a building, whatever. Costs them $2,000 for the day anyway. That's the b. A, right? The lowercase a here, as I mentioned, was slope. So that lowercase a, again, I'm writing down here, was the slope. And it's the change in the cost per change in bicycle. Right? Again, the independent variable, the input is x. That's in the change in that is in the denominator of the slope. The dependent variable is the cost, the c, and the change in the dependent variable, the change in the cost, is in the numerator. And as I mentioned, this is in dollars per bicycle. Well, again, looking back through the problem, as I said, look at these last couple sentences. I talked about, it costs $80 to manufacture a bicycle, but on top of that, they must pay $1 in tax for each bicycle they produce. So it costs them $81, right? The $80 plus the $1 of tax to produce one bicycle. And 81 divided by 1 is simply 81. Right? So it's 81, dollars per bicycle. We do, dividing the units here. So that's our slope, this rate of change. How much does the cost change when I change the number of bicycles manufactured? All right, so popping that in, the cost of producing X bicycles is, I'm replacing A here with 81. Right? This is $81 per bicycle, and then that gets multiplied by the number of bicycles. So can you see how that would get rid of bicycles, right? If I take dollars per bicycle, dollars in the numerator, bicycles in the denominator, and multiply by the X bicycles being produced, bicycles would have a unit cancellation and you'd be left with dollars. So this gives me how much it costs them to manufacture X bicycles. But remember, on top of that, there was that $2,000, so plus the B plus the $2,000, just for starting up the business that day, right? Again, that could be a rental cost for the building, that could be the cost of labor, that could be the cost of just the cost of the equipment to manufacture the bicycles, right? This $2,000 for a day has a lot of things that could possibly go into it. And there we go, right? There's a nice linear function, right? It has that mx plus b or ax plus b form, where input is x, input is the number of bicycles, and the output is c, or c of x, and the cost is calculated this way. Wonderful. All right, now I'm going to use this, right, for part B. All right, so I'll slide this up. We have a model for the problem. I'll go back to the problem later. All right, part B. Now that I have my cost function, cost written as a function of x, the bicycles produced in a day, the part B is, what is the cost of manufacturing 5 bicycles in a day? All right, so look at the question here. What is the cost? So they don't know what C is, right? Or C of X. You could write either one of these, right? This could also be written as C equals 81x plus 2000, but I like the function notation so we know what the input is. But you could say, what is the cost? So they don't know cost. C equals what? C of X equals what? Of manufacturing 5 bicycles in a day. So 5 bicycles are manufactured. And that was what X represented, right? The number of X represents the number of bicycles manufactured in a day. So they're telling me, X equals 5 here. What is the C? What is C of X? So another way this question could be asked is this. When X equals 5, what is C of X? Right? Or just what is C? Right? What is the cost? All right. So really all we're doing here is taking our linear model, our linear function describing this situation, and finding what's the cost, replacing X with 5, right? My input with 5 bicycles produced, going through and seeing what's the cost of producing 5 bicycles a day. That's what this means. The value of C at 5, or the cost of producing 5 bicycles a day, is, and then again replacing X with 5 here, $81, right? The $80 plus the dollar in tax, times the 5 bicycles that are produced, right? Replacing X with 5. And then on top of that, plus the $2,000 it costs for a day just to run the business. All right, and then we do some order, multiplication here. 5 times 81 would be 405, and then plus the 2,000. So I'm getting here 2,405. And don't forget this is the cost of C. That's dollars, right? Cost was in dollars. Great, and now I'll bubble it here, but this is not how I'm going to answer the question. All right, I've said this in other videos if you've been watching on word problems, application problems. When you're asked a question in a word problem, you should answer in complete sentences and have units on your numbers so that they have meaning. So the question was, what is the cost of manufacturing 5 bicycles in a day? The way I would answer that question is this, right? So the final answer is a nice full sentence. The cost of manufacturing five bicycles in a day is, as we saw, $2,405. And this is how I would answer the question, right? In a complete sentence where every number involved actually has meaning because there are units attached to them. You know, five what? Bicycles, right? There's the units on five. 2,405 what? Dollars, right? There's the units on 2,405. And it's in a nice complete sentence, easy to read. And I guess you could also just write, it costs $2,405 to manufacture five bicycles in a day. I mean, it would probably take as much time to write. But please, you know, I want you to get in that habit, you know, nice properly answering questions. Nice full sentence, and throw units on your numbers to give them meaning. All right, next question. Again, using the same model, right? Our linear function here for this situation, for this problem, this c of x equals 81x plus 2,000. And now I'm asked this question in part C. How many bicycles can be manufactured for $2,810? All right, so see the how many bicycles? This is what's x? All right, how many bicycles can be manufactured? I don't know. They don't know the number of bicycles manufactured, and that's what x represents. X was the number of bicycles manufactured in a day. For this $2,810, this is the cost. So c of x equals 2,810, or just c equals 2,810. They're giving, so this is the other way around. You know, part B, I was given x and had to find cost c, or c of x. Here I'm given the cost c, or c of x, and I have to find x. So what we're doing here is basically solving this equation for x. This c of x, you know, when is or I guess I could say another way to ask this question is, you know, for what value of x is c of x going to be equal to 2,810? Right? This is just another way to ask that same question. And so what we're doing here is solving this equation, you know, c of x equals 2,810. Solve this equation for x. All right. So what does this equation look like with x, a term with x in it? You know, what is the cost of producing x bicycles? This c of x on the left side. Well, the cost of producing x bicycles in a day is given by my formula here, my equation from earlier in part A. All right. So that this c of x on the left side looks like this. This is 81x plus 2,000. And equal, you know, when is that equal to the $2,810 on the other side? All right, and then this is a very simple, you know, linear equation. Get all the terms with the x on one side, terms without x on the other. So I'm going to take away this 2,000 from both sides, leaving me with 81x on the left, and, you know, 2,810 minus 2,000 is 810 on the right. And then I want x alone, right? So I'll get, you know, multiply both sides by 1/81st, or, you know, simply divide by 81, same thing. And the 81s divide out to become 1 on the left, so I have x equals x on the left equals, and then, you know, this is, hopefully you can see that this is 10, right? 81 times 10 would be 810. Again, I'm going to do this a little bubbly here, but this is not the answer. Right. I mean, it is the answer, but it's not a nice full sentence. So the question is, you know, how many? Oh, and then don't forget, of course, when you're solving an equation, don't forget to check the solution. Right. So let's go back, plug in 10 here. You know, 81 times 10 is 810 plus 2,000 would be 2,810. It works. It checks out. Okay. So don't forget to check solutions, when you're solving equations, please. All right, so now that I know that 10 is the solution to this equation, how would I answer the question? It's how many bicycles can be manufactured for $2,810. I'm getting x equals 10. Remember, x represents the number of bicycles. So the answer to the question, I would write out, 10 bicycles. And we're seeing 10. 10 bicycles can be manufactured for $2,810. And if I was asked this problem, in a homework assignment and whatnot, this is how I would answer. In a full sentence where numbers have units. 10 has the word bicycles attached to it, so you know what it means. 2,810 has dollars attached to it, so you know what it means. Right? Numbers have units attached so that there's meaning behind the statement. Okay. Then the last part of this particular example, right, I'll get into one more after this, one more example with several parts. I'm going to make a graph. Right? Graph the linear function. Right? So I've already made my axes here on some graph paper. I mean, you don't need to use graph paper. Just make sure you're drawing your axes as straight as possible so they cross at a 90-degree angle or as close to a 90-degree angle as you can make. And properly label things and make sure that that when you're labeling distances on the axes that you're consistent, that all the squares, all the notches you make represent the same number of units. Okay. So looking at this equation here, looking at some ordered pairs, I'm noticing that if I'm asked to graph this linear function, it's a line, it's got that form ax plus b or mx plus b, so I know the graph's going to be a line. And to graph a line, you only need two ordered pairs, 2 points. I think a very easy one to find would be the c-intercept. Notice remember the horizontal axis usually represents the input variable, the x here. The vertical axis typically is reserved for the used to represent the output variable or the dependent variable, which is the cost, c. Now you can also call this y if you want. There's nothing really wrong with that, but I'm going to call it c for cost. And then I'm going to have my squares. Each square represent a consistent number of units. So what I'm going to do is each square on the x-axis, I'm going to have it represent 1 unit, 1 bicycle. All right, remember this is x bicycles produced. So this is 1 bicycle, no bicycles. I'm not going to go into negatives, right? Because negatives doesn't make any sense. Right? It doesn't make any sense to manufacture negative bicycles. What does that even mean? How could you produce -1 bike, -2 bikes? So 0 bicycles is just make nothing. Then 1 bike, 2 bikes, 3 bikes, 4 bikes, etc. All right, so I'm going to have each square on the horizontal axis represent 1 bicycle. And then notice the costs. The cost is going to start off at $2,000, right? Think about it. When I put in 0 for x, what's that term disappears, the 81x, 81 times 0, 0, and I'm left with $2,000. So I'm plotting the ordered pair 0, 2,000. Now you could have each notch represent $1,000, but another thing I'm noticing too is that, remember, the slope is 81. So every bike I create, every bike that's manufactured, is only going to bump up the cost by $81. So if I have each notch represent $1,000, I'd move right 1 and then up 81 for the slope, and that's like less than 1/10 of 1,000. It'd be very hard to see that transition. Right. So what I'm going to do here is I'm going to have each, okay, first off, you might see this on some graphs. I'm going to have each square here, I'm going to have each square represent 50 units, okay? Just a nice round number, and you know, that way you'll actually see a little bit of a slope in the graph when you have to go up 81. Right? Now, even if I let each one represent 50 units, you know, to get to 2,000 would take a while, right? Would be a lot of squares up. So you might see this in some graphs where if you want to make a big jump in the axis, like I'm starting down here at 0, and then somewhere along the axis you'll see this like zigzag looking shape, and then it keeps going. This little zigzag on an axis just means you're jumping a lot of values, you know, a big jump in values. All right. So I'm starting here at 0, and then I'll say let's have 2,000 start here at this square. All right, and that's totally fine. So I jump 0 and then 50 and then blah, 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 and then it went high up, high up, high up, and then there's 2,000. So you see this little zigzag thing in the axis. And like I said, I'm going to have each square from then on out represent a distance of 50 units. So there's $2,050. Remember, this is in dollars. This is the cost. $2,050, you know, $2,100, $2,150, $2,200, and so on. All right, just so long as I'm consistent. All right. All right. So now let's plot some ordered pairs. Plot some points, input and output relationships. So as I mentioned, if I made no bicycles, right? If X were 0, the output would be 2,000. You know, it costs $2,000 to create 0 bikes, and let me label that. All right, let me label that ordered pair. So here's the ordered pair. You know, 0, 2,000. Right, sorry about the tininess of that, but that's 0.0 2,000. 0 input, 0 bikes, 2,000 output. You know, costs $2,000. Now I could use the slope. Remember, the slope is 81, which is 81 over 1. So I would rise 81, so go to 2,081, so somewhere between 2,050 and 2,100, and then write 1 unit. Or I could plot a point that we've already actually discovered, right? We've already seen a few input-output relationships. If you go back to part B, it said, what is the cost of manufacturing 5 bicycles in a day? And that was $2,405. So that means input 5 for X, output 2,405 for Y, for C, right? So let me plot that. All right, so I got 5 for X, 2,405 for the C. All right, so there's 2,200, 2,250, 2,300, 2,350. There's 2,400, 2,450. All right. Now 2,405 is just going to be a little bit above. You know, it's a tenth of the way between these two, right? $5 is 1/10 of $50. So a little bit above 2,400 there. So input 5, output 2,405. So a little bit above the 2,400 mark, over in line with the 5 units, so like right there. That is a point that we discovered, and I will label it so we can actually know what the ordered pair is. So 5, 2,405, right? And that should be enough, right? Like, we know it's a linear function, a line, so if you have 2 ordered pairs, you should be able to draw the rest, and I will do that right now. So let me pull a ruler here and line up these points, centers of these points. I'll draw in this function going through these points, and it would go that way forever, right? So because theoretically I could produce as many bicycles as I want in a day. But notice I didn't continue it on this way, right? I just started from this point, 0, 2000, and went up there. Because, as I said earlier, if I continued to the left here, if I drew it going down, that would imply that I had, some points with a negative x value. That means I would have created negative bicycles, and that doesn't make any sense in the context of this problem, right? It doesn't make any sense to create or produce negative bicycles. So great. There's the graph of that linear function. Now another point that would be on this, right? We saw in part D, or part C, my apologies. See, I had x equals 10. C would be 2,810. So if I went to x equals 10, right, if I went to 6, 7, 8, 9, 10 bicycles, the output up here, this point here, should be at $2,810 on the vertical axis. Right, so there's the point, 10, 2,810. Right, 10 bicycles, it costs $2,810 to produce. But it should fall on that line. All right? Great. All right, so that's one example. And the example I have after this is kind of similar, only we're not given the model, the c of x equals ax plus b. We're still going to use that same model to go through my next example. Alright, so my next example is about somebody making monthly payments on a car. Alright, so here I have Roberta's monthly payments for her new car are $250 a month per month. She estimates that maintenance, right, so like oil changes, tire rotations, whatever, car washing, why not? She estimates that maintenance and gas cost her 18 cents or $0.18 per mile driven, right, per mile that she drives. Alright, so part A is like part A in my last example. It says write a linear function, right, linear, that expresses the monthly costs, right, so the cost of driving this car in a month, just 1 month, the monthly cost C of operating the car as a function of miles driven x. So I want to write an equation where C equals and then an expression with x in it. That's what they mean. Well, whenever they tell you to write one quantity as a function of another quantity, they just mean write C equals and then some expression that depends on x. Okay. So they told me to write a linear function. I know what those look like. So I'm going to have C, the cost of driving X miles, right? C of X. So this is now the cost of driving X miles will be equal to some slope called A or M times X, and then plus, some fixed cost B. Where we need to fill in, I need to fill in A and B. That lowercase a and lowercase b. All right. All right. And again, this is the cost of 1 month's driving, right? And driving X miles. All right. So look back through the problem, and I'm noticing, it stated that it costs her $250 for a month. So that's without even driving, right? So driving 0 miles costs $250, right? If she didn't drive at all, it would still cost her that amount of money. All right, so let's think about that here. That means that A times 0, right, replacing X with 0, 0 miles, right? That's what this driving 0 miles means, plus B would be equal to 250, the cost, right? This is the C, right, the 250. So that means B, that lowercase, a times 0, anything times 0 is 0. So the value of b is 250. All right. So now we have this. Now we have c, the cost of driving x miles in a month is, some value a that I still don't know, times x, plus, and now we know the value of this b must be 250. And that was just the cost of, having the car for a month without even driving. All right, now the a, that's the slope, and notice how it's multiplied by miles, right? X is in miles. So I want a cost though. What's the cost per mile, right? Remember the slope is a rate. Right? It's the change in cost over the change in miles, right? A is the slope. It would be the change in the cost divided by the change in the mileage, right? Which will be dollars per mile, right? If you add units to this, because they throw dollars on costs and they mention miles here, miles driven, right? So what does it cost her to drive per mile that and it said back in the problem, it said it costs her, she estimates that it's costing her 18 cents or, $0.18 per mile. So that is the slope. That's the A. All right. Okay, so now I can fill in the model and be finished with part A. So the cost of driving this X miles per month in a month is, the 0.18, right? It cost me 18 cents per mile, or $0.18 per mile, and then I multiply that by the number of miles driven, and then the miles units, you'd have miles in the numerator with the X, and miles in the denominator with the A, and miles would cancel and I'd be left with dollars. So this is the cost of driving X miles. And then on top of that, the $250 monthly cost, right? The cost for just having the car for the month. Okay, great. There is our linear function describing how much it costs to drive X miles in a month with this new car of Roberta's. Right? Okay. So there's this function, and what I'm going to do is, again, just, the rest of the parts are pretty similar. Now part B is a little different, right? But after that it's pretty similar to my first example in this video. So part B is, what is the domain? Right? What is the domain of this linear function? Now remember, domain is the set of all the inputs that can be used. Now my input here is X, the output is cost, C of X is C. Right? So the domain is the set of all the values of X that can be used here. Now be careful. Remember, in context, it matters. If I didn't have this word problem, if these words weren't expressed, if these were not written down, and I said, just look at this function here. C of X equals 0.18X plus 250. And I said, what am I allowed to plug in for X? What is the domain? You would say it's all real numbers. You can plug in whatever you want for X. You're never going to be dividing by 0. Right? There's no denominators here with a variable in it. There's no even roots. There's no logarithms. I would say that the domain was all real numbers. But this is a word problem. This is an application problem. You have to take into account the context of the problem. Right? These numbers have meaning now. And this is, driving a car. And remember that X is the number of miles driven. So when I say what values can I plug in for X, it's what values make sense to plug in for X. Does it make sense to plug in negative numbers here? No, right? What does it mean to drive negative miles? Even when you drive backwards, you're still going a positive distance. Distance is distance is non-negative. So this number of miles can't be negative. This is non-negative. All right, can't be a negative. I can't plug in negative numbers here. It makes no sense. So based on the context of the problem, I would state that the domain of this function, okay, the domain of function c, this c of x function, is, I can use any x I want, and I can plug in any x I want as long as, right, a little set notation here, I can plug in, my input variable is x, and then after the bar here I put a little description. What can I use? As long as they're non-negative, as long as x is greater than or equal to 0. That's what it means to be non-negative. You could have also written out the words x is non-negative, but saying this inequality means the same thing. X is greater than 0, a positive number, or x equals 0, but never less than 0. Additionally, too, if you want to put this in what's called interval notation, that's, left endpoint would be 0, right endpoint, there is no highest value, there is no highest non-negative number, so I indicate that by an infinity symbol. Always parentheses on infinity, capping off the infinity, because infinity is not a number. So, we cap that with a parenthesis to indicate that, this is not actually part of the set. It's just an idea to indicate that there is no largest value. And then 0 is, I can plug 0 in for x. Right? You can drive 0 miles. That just simply means you didn't drive. So because 0 can be in the domain here, it can be plugged in, it's in the domain, and to indicate that it actually is in the domain, we use the rectangular bracket. And again, if you want to look up other videos on interval notation, please do, but this is very brief. Okay, so there's the answer to this question here. Right? The domain of this function is the set of all non-negative real numbers. Right? You can only, when you're driving, you can only drive non-negative distances. Doesn't make sense to drive negative miles. Great. Then part C. All right, my next question. So now here's where it gets to be like the last example, my first example from this video. So I've got the model, right? It costs $8.18 per mile. I'm driving X miles, and then add the $250 cost, right, for the monthly cost. And the question here is, what is the monthly cost of driving 320 miles? So look at what's unknown here, right? What is the monthly cost? That's the C, right? They don't know that. Or the C of X, right? That is unknown. What is this monthly cost? What is the value of C, or C of X, of driving 320 miles? So they drove 320 miles. And remember, X represents the number of miles driven. Okay? So this 320 miles is the value of X. Right? So another way to ask this question, you could ask, when X is 320, what is C of X? Or what is the value of C? So what we're really trying to find here is just simply, when I go through this rule and plug in 320 for my input, the cost of driving 320 miles in this month, right? What is C of 320? I just replace X with 320 throughout the rule, throughout my model. And the cost of driving 320 miles is, 0.18 times 320. And then plus 250. Okay, and you can set up, multiplication and whatnot, do it the long way. I'm just going to punch this in real quick for the sake of brevity. So 0.18 times 320 plus 250. So the cost of driving 320 miles is $307. And it says 0.6, and then so that's 60 cents. Right? Remember, this is a cost. I put the little units on there if you want, but again, I'm going to kind of bubble this, but that's not the answer. I want to write it in a complete sentence. So what is the cost of driving 320 miles? here's the answer. Right. So the way I would answer this question is the monthly cost of driving 320 miles is, and then this, $307.60. And again, this is how I would answer it if I was, given this problem in an exercise or as part of a, part of a test or something. All right. Additionally, something else that I can point out here is if we were to go on the graph, right? So if I look at this here, that means that on the graph of this function, on the graph of C, we would have this ordered pair. Now remember, my input variable is x, output C, so the input is mileage, which was x, 320, comma, output is cost, 307.60, right? I would have this ordered pair. I'd plot this point if I'm going to, and I will be getting to the graph of this function, this cost function, later. So we should see that indeed this point should be on that graph. Okay. So the next part, now, part C, I was given a mileage and asked for a cost. Part D is the other way around, right? So how many miles, so right away I'm seeing they're asking for X, right? How many miles means, they don't know what X is, right? Because X was the number of miles. How many miles can Roberta drive each month or in a month? If she can afford the monthly cost to be $282.40, right? So this is the cost. So C equals 282.40, or you could say C of X equals 282.40, and this is the equation that we're solving. All right, and then again, another way that you could ask this is, for what value of X is this a true statement? This here. So we're going to solve this equation, C of X equals 282.40, right? That's a decimal point. So we're going to solve this for X. All right, so what is the cost? Now, what is this C of X on the left? The cost of, driving X miles is given by our equation here. So that the left side is, 0.18 times X plus 250 equals, and then the other side is, the $282.40, right? It's 0.40. All right, so I have this equation that, I want to get all the terms with X on one side, all the terms without X on the other. And if you'd like, some people tend to not like working with decimals. All right, and I've done this in videos before, where if I want to move, if I want these to be whole numbers with the decimals here, I would need to move both of them to the right, two decimal places. And to move a decimal point to the right 2 decimal places requires multiplication by 100, right? You multiply by some power of 10 to move decimal places around, right? So I'm not going to go into more depth than that, right? So I'll just see. I'll do that. Let's do that. And I'll multiply 0.818 this whole left side. I'm going to multiply by 100. And there are 2 terms over here, so that's going to be requiring some distributing. Each of those terms, the entire side, gets multiplied by 100. And then same thing for the value on the right side. Now there's only one term on the right side, so again, we're just multiplying by 100. All right. The 0.18x times 100 times 100 moves a decimal place to the right twice. That's 18x plus, and then 250 times 100 just adds 2 more places, adds 2 more zeros. 20. That'd be 25,250 with 2 zeros added. Equals, and then the other side again, just the decimal place moves right twice. You're multiplying by 100, so that's 28,240. All right, now I have this equation that doesn't have decimals involved. People tend to like that more. It looks cleaner. do what you want. You could have left it this way as the decimals and then subtracted 250, then divided by 0.18. But I'm going to subtract now the 25,000 from both sides, giving me 18x on the left still, and then 28,240 minus 25,000 is 3,240. And then we divide by 18, right, to get the x alone, or multiply by 1/18. All right, so on the left side, the 18s divide out, and I'm left with, sorry, I'm just going to pull this up here. The 18s divide out, I'm left with x. And then on this right side, again, you can set up a long division thing or use a calculator. Doesn't matter, right? So if we do long division, 18 goes into 32 once with 14 left over. Drop the 14, and then the next 4 would be 144. And then 18 goes into 144. Let's say 6 times. Yeah, 6 times, because it'd be 60 plus 40, 108. No, it would be 7 times. Yeah, 7 times, because 7 times 20 is 140. This is even less than 20. So 7 times, maybe 8 times. Yeah, it's 8 times. 80 plus 64, 144. So it's looking like 180. Right, 180. 18 squared is 324. Silly me. Anyway, so 3240 divided by 18 is 180. Right. So x equals 180. Now remember, x is numbers of miles driven. Right? You can throw miles there. Now this is going to help me answer the question. I remember what the question was. I'll kind of clear this stuff out here. How many miles can Roberta drive each month if she can afford the monthly cost to be $280.42? And I'll just answer this way with a complete sentence, right? I'll say she can drive 180 miles. I guess you could also say up to 180 miles, because if she drove less than that, she could still afford it. But she can drive 180 miles each month if she can afford a monthly cost of $282.40. Okay, that's how I would answer it in a nice full sentence, right, where the numbers that are mentioned have units. Okay. All right. And another thing to point out too, we're going to be getting to the graph here in a second. If you were looking on the graph of the function, that cost function c, right, this c of x equals 0.18x plus 250, you would have this ordered pair, right? Now remember, the input is from the independent variable, the x, right? So you'd have 180 miles for the input, 180, comma, and then the output would be the cost 282.40, right? So you'd have this ordered pair to plot. All right, wonderful. All right, so let's get to it. That's the last part of this video, is making the graph of this cost function. All right, so there's the cost function. I'll leave it up here. C of x equals 0.18x plus 250, and part E is make a graph of this thing. Now I've already written my axes. Horizontal axis represents the miles driven, x. The vertical axis, the cost, c, or c of x. And then notice how I have the bulk of it up here in the upper right quadrant, where I have positive x values and positive costs. Because again, I said at the part B with the domain, right? It doesn't make sense to have negative miles driven, so that's why there's not much of the negative x-axis. Same thing for the negative costs, right? It doesn't make sense to pay negative money, Right? And it's not like they're going to be giving you money to have the car. All right, so that's why I'm mostly over here. All right, so some points to plot. Now, before I get to point plotting, let's talk about how I'm gonna label each square. So what I'm going to do is I'm going to have because just noticing some points that we had to. I've got 180 here for the x in part D, and in part C, I had a point with 320. So what I'm going to do is I'm going to have the squares on the x-axis just represent 10 miles each. Okay, so there's 0 miles, right? And then 10, 20 miles, 30 miles, 40, and so on. All right, so then for the costs, again, the costs here, the initial cost is going to be $250, right? It's going to be $250. But then after that, think of the slope, right? It's $250 if I drive 0 miles, right? If I plug in 0 for x, that'll be gone, and you'll have 250. So I'll have 0, 250. But then look at the slope. The slope, this tells me that every mile I drive is only going to bump it up another 18 cents. So that means every 10 miles I drive will only bump up the cost $1.80, right? If I multiply that by 10, 1.8. So what I'm going to do is have each notch here, each square, represent a distance of just $2, right? Noticing because my one squares down here is 10 miles, and every 10 miles will increase the cost by $1.80. All right, so I'm going to have it be a nice round $2. Right, and so if I have each square be $2, to get to 250 for when there's 0 miles driven, that'd take a while. So just like in the last example, I'm going to have this little zigzaggy thing to indicate again that we're making a big jump. All right, so here's 0, here's 2, here's 4, and then I jump way up, and I'll have this square here represent $250 of cost, and then I'm going to go every $2. All right, so 252, 254, 256, etc. All right, have every notch, every square represent $2. Okay, so as I said, if I drive 0 miles, you plug in 0 here, you're getting 250. So 0, 250. And then, I'll just do a couple of these. I plug in 10. You can make a table if you want. When I plug in 10, right, that'll make this 0.18. 1.8, sorry, 1.8, and then I'd have 251.8. So just barely under 252. There'll be a point there. Now I think an easier point to plug in will be 100 when I plug in 100 miles. So here's 50 miles, 60, 70, 80, 90. Here's 100 miles. All right, 100 miles. When I plug in 100 miles driven, 0.18 times 100 would just be 18. So then 250 plus 18, and again I should label these points, but 250 plus 18 would be 268. So here's 0 miles driven, cost $250 for that month, 0, 250. 100 miles driven will cost 268. So here's 258, 260, 262, 264, 266, $268 right here. So we're talking this location, a nice on the edge of a square, on the corner of a square on my graph paper. All right, I'll label that point. So if I drive 100 miles, it's going to cost $268. for that month. And knowing that this is a linear equation, it has that form mx plus b, y equals ax plus b. I can draw in the rest with just 2 points, right? You only need 2 points to determine a line. So I'm going to line up the centers of these, and here we go. All right, there we go. There's the cost function c. Right? Wonderful. And some of those other points that I described earlier, like the 180, 282.4. Right, there was this 180, 282.4. That would be on this graph. If I went out to 180 miles, right, just go 8 units more to the right there, 110, 120, 130, 140, 150, 160, 170, 180, and see where, I didn't continue it on far enough, but if I put that point on the graph up there, you'd have 180 and then 282.4. Right? It'd be between 282 and 284 on my c-axis. All right, wonderful. All right, so again, hopefully it's not so bad, right? I know the whole how do I spread my notches out? How many units should they be apart, and when should I do this? That just takes experience, to be honest. Take a look at what your y-intercept's going to be. I knew it was going to be at 250, and then keep in mind the slope, and also how far apart you're making your notches on the horizontal axis to determine what would be a reasonable distance between my notches on the vertical axis. I didn't have to make these 2 units. I could have made these all 1 unit apart and started at 250, and I would have gotten a line that was not going up so fast, but it still would have been going up because you have a positive slope. It's up to you. Right? It takes practice, takes some experience to get reasonably good at deciding what notch distances would be best. All right. So that was a long one. I know a couple examples there where you use a linear function in a word problem and an application and answer some questions about it. But it's no different than any other linear function video I've put up. Right? Just had some word problems in it. All right. And as I like to say at the end of these, try your best. Do the best you can to learn the material, understand the material on your own before you go looking for help. Because I find that people, for people, material tends to stick with them better and for longer, and they have a better recall of it when they've taken the time and effort to learn it on their own. So read the material, read the author's examples, perhaps even work on author's examples and try to figure out, write your solutions to the examples before you see how the author did it, and then compare your work to the author's, and maybe you can learn from mistakes that way. Practice problems, practice exercises that are provided, of course, and look up solutions when they're provided, if they're in the back of a book or something or on some worksheet, just to check yourself, see how you're doing. And don't just give up after the first attempt. If after several approaches at a problem, you're still not seeing how it can be done, still not working out for you, perhaps you should read through the material again, maybe even a 3rd time. Because you might have missed something, maybe read it a little more slowly, a little more deliberately. And perhaps on that 2nd or 3rd read through you will catch something, or something will make sense that didn't make sense the first time through. But if after that, if after several read-throughs of the material and several attempts at problems you're still not getting it, it is not a sign of weakness whatsoever to go asking for help. That is what other people are there for. Ask a teacher, a tutor, a friend, someone in the class who you know that knows the material well and is willing to help. Look up supplemental materials online. There's loads out there. Look up videos on the subject you're studying, like this one, or plenty of other ones out there that are better than this one, I assure you. I know they're out there and they're easy to search for. But just keep at it. Stay persistent. Keep practicing. Don't give up. And as easy as it is to say, it's easier said than done. Try to have a positive attitude. Try to say you're going to enjoy this. You're going to take something from it and not hate it. Because it's amazing the difference that can make. Just a change in attitude towards the subject. So keep persistent. Keep practicing. Stay positive. And I just know you're going to get it. and don't give up. All right. And thank you for watching.